Topic 3, thermal physics. We're going to start with modeling a gas pressure. Consider a gas molecule confined in a closed box as shown. Since the molecule's direction is always changing, it is accelerating and thus feeling a force from the wall of the box. Based on Newton's third law, the molecule is exerting an equal and opposite force on the wall of the box. So the pressure is defined as force per unit area, and the unit is Newton per square meter or Pascal. We have an example. 150 kilogram man stands on a foot on some ice. Given that his foot is about 9 centimeter by 10 centimeter in rectangular cross section, find the pressure on the ice. The force he exerts on the wall is the weight of the man. So that is F equals to mass times the gravitational field strength. Mass is 150 and the gravitational field strength here is 10, so 1500 Newton. And the area is length times width, which is converted into meter, 0.09 meter times 0.1 meter, which gives us 0.009 square meter. Finally, the pressure equals to force over area. That gives us 170,000 Pascal. If the ice is thin enough that it will break under a pressure of 1 times 10 to 5 Pascal or 100,000 Pascal, what should be the area of the snowshoe that will just prevent him from breaking through when on 1 foot? We know the pressure equals to force over area. Now the question asking the area. Area equals to force divided by pressure. And the force, the weight of the man did not change, so that is 1500 divided by the pressure, now 100,000. That gives us 0.015 square meter. An ideal gas is an imaginary gas that is used to model real gases and has a following properties. The molecules that make up an ideal gas are identical perfect spheres, are perfectly elastic, which means they don't lose any kinetic energy during their collision with each other or the wall of the container, and it has no intermolecular forces. Their potential energy does not change. And the molecules that make up an ideal gas are so small that their volume is much smaller than the volume of their container. Temperature is a measure of the random kinetic energy of molecules. If the temperature of the gas increases, so does the average speed of the molecules. Let us take a look at the animation. Lower temperature, medium temperature, and high temperature. This shows that temperature is a measure of the random kinetic energy of the molecules. We can see that if the speed of the molecules increase, then the number of collision with the container walls will also increase. Thus, the pressure will increase if the temperature increases. That means pressure is proportional to temperature. So consider small, medium, and large containers. In a small volume, the molecules have a less distance to travel to hit a wall. Thus, the wall is hit more often, or the frequency of the collision with the wall increase. Thus, the pressure will be bigger if the volume is smaller. Let's take a look at the following interesting scenario. Consider a syringe full of an ideal gas. If we make the volume less, we see that the temperature will increase. Since the plunger exerts a force on the gas and executes a displacement, it does work on the gas. We know from the work energy theorem that if we do work on the gas, its kinetic energy must increase, as work done equals to change in kinetic energy. If we do work on a gas, its kinetic energy must increase. On the other hand, therefore its speed will increase, which means its temperature increase. On the other hand, if the process is reverse, the gas will do the work and lose kinetic energy and cool. Here's the MCQ question. A temperature of an ideal gas is reduced. Which one of the following statement is true? We know temperature is a measure of the average kinetic energy of the gas. So when the temperature is reduced, the average kinetic energy also reduced, which means reducing the kinetic energy reduces the frequency of collision. So the correct answer should be the molecules collide with the wall of a container less frequently. So definition of the mole. One mole is the number of atoms of an element that will have a mass in gram equal to its atomic mass. Find the mass of 1 mole of carbon-12. 1 mole of carbon-12 has a mass in grams equal to its atomic mass, which is 12 gram, which is 0.012 kilogram. Avogadro constant. A mole of carbon-12 and a mole of phosphorus has the same number of atoms. Na equals to 6.02 times 10 to 23 molecules. So 1 mole of any substance contains this amount of molecules. Let's take a look at how many atoms of phosphorus 31 are there in 31 gram of it. So mole number equals to mass divided by molar mass. Mass is 31 gram given, and molar mass is 31. So that is 1 mole. And 1 mole of any substance contain Na, which is 6.02 times 23 molecules. How many atoms of phosphorus 31 are there in 145.8 gram of it? So mole number equals to mass divided by molar mass. Mass is 145.8 gram. And molar mass is 31. That gives us 4.7 mole. Mole number equals to number of atoms divided by Avogadro constant. Number of atoms equals to N times Na. 4.7 times 6.02 times 10 to 23 equals to 2.83 times 10 to 24 atoms. A sample of carbon-12 has 1.28 times 10 to 24 atoms as counted by Marvin, the paranoid android. A. How many moles is this? B. What is its mass? So let's take a look at A. Total number of atoms given, and we would like to find mole number. That's mole number equals to total number of atom divided by Avogadro constant. So N divided by Na. N is total number of atom, 1.28 times 10 to 24. Avogadro constant is 6.02 times 10 to 23. So that gives us 2.13 mole. And we're going to find the mass. So mole number equals to mass divided by atomic number. And the mass equals to mole number times atomic number. So 2.13 times 12, which equals to 25.6 gram. The equation of a state of an ideal gas equals to PV equals to nRT. So P is pressure, V is volume, N is number of moles, and T is temperature. And pressure is in Pascal, volume is measured in cubic meter, and temperature is measured in Kelvin. An ideal gas is kept in a container of fixed volume at a temperature of 30 degrees Celsius and a pressure of 6 atomic pressure. The gas is heated at constant volume to a temperature of 330 degrees Celsius. The new pressure of the gas is about. So it's ideal gas. We're gonna use ideal gas equation. PV equals to nRT. We need to convert degree Celsius into Kelvin. So temperature in Kelvin equals to temperature in degrees Celsius plus 273. Initial temperature 30 plus 273, that is 303 Kelvin. Final temperature is 330 plus 273, that is 603 Kelvin. We also know that it's constant volume. Volume initial equals to volume final. So we have initial state and we have final state. Initial state divided by final state, we have this. Constant volume, so volume cancel out, is a fixed number of gas, so N's cancel out, R cancel out, and we have the final pressure. So final pressure equals to initial pressure times the final temperature divided by initial temperature. We plug in the values. 6 times 603 divided by 303 equals to 12. The correct answer is C.